Good morning, students. Next topic is signed binary numbers. Unsigned representation can be used for the positive integers. How about negative integers? Everything must be represented in binary numbers. Computers cannot use minus or plus signs. Okay. In negative binary numbers, there are three different symbols like systems have been used. The first one is signed magnitude, 1's complement and 2's complement. And see here, for negative numbers, the sign bit always is 1 and positive number it is 0 on these three systems. Okay. Signed magnitude, the leftmost bit is the sign bit, 0 is plus and 1 is minus, and the remaining bits hold the absolute magnitude of the number. See here, 47 2, 4, 8, 16, 32, 0 and is a 47, but here we can assign minus, the sign bit is 1, so it is minus, and sign bit is 0, it is positive. Okay, 1, 2, 4, 8, 32, 15 plus 32, 47, but you can assign the sign bit is 1 because of it is 0, like it is negative. See here, 0 is plus and 1 is minus, so 1 is minus, 0 is plus. For 8 bits we can represent the signed integers. For example, this minus 1282 plus 127. Okay, so the leftmost bit is the sign bit and the remaining bits hold the absolute magnitude of the numbers, that is 0 is plus and 1 is minus. Okay, so here the 47, 1 here assigned is the minus, 0 is assigned is the plus. Okay, and 1's complement, replace each one by 0 and each 0 by 1. For example, minus 6, so first represent 6 in binary format, 3, 4, 5, 6, 7, 8 digits, 0, 1, 1. Then replace 1, 0, 0, 1. And 2's complement, find 1's complement, add 1. Example is minus 6. First represent 6 binary format and 1's complement and 2's complement. Okay, 1, 1, 1, 0. Okay, then arithmetic addition usually represented by 2's complement. See here, plus 5 and 11 is the 16, plus 5 minus 11 it is, we can assign to the 2's complement, then minus 6 is here, then minus 5 to the 2's complement and plus 11 plus 6, that is the bit, minus 16 is the discarded bits. Okay, then register. So what is mean by register? They can hold group of binary data. It is called as registers. Data can be transferred from one register to another. It is and fixed point representation. See, this representation has fixed number of bits for integer part and for fractional part. Here you can assign the two parts, first integer part, fractional part. For example, if given fixed point representation is 1111 dot fff, then you can store minimum value is 000.00 and maximum value is 999.99. Therefore, three parts of fixed point number representation is sign field, integer field and fraction field. Okay, see here two types. Unsigned fixed point you can assign integer and fractional, and signed fixed point you can assign sign, integer and fraction. Okay, see, for assume that a number using 32-bit format which reserve 1 bit for the sign and 15 bits of the integer part and 16 bit for the fractional part. Okay, see, then minus 43.625 is represented as likewise. So sign bit is 1, integer part and fractional part. Okay, it is a 625 43 minus, where 0 is used to represent plus and 1 is used to represent minus. Okay, and here all 0, 1, 1 is a 15-bit value for decimal 43 and 16 is the fractional part of 0.65 is the fractional part, it is the integer part 43. Here is the sign bit, so minus is sign bit. Okay, plus is 0 and minus is 1. So in fixed point representation, it is the two parts. First is the integer part and fractional part. Okay, in fractional part, go for the signed fixed point and sign and integer and fractionals. Okay, see, assume the number 32 bit and with the values minus 43 and 625. In the fractional part is 16 bit binary value and integer part is 43. Okay, then one is a sign bit, that is minus is used for the sign. Okay, and this representation does not reserve a specific number of bits for the integer part or the fractional part. Instead, it reserves a certain number of bits for the number that is called as a mantissa or significant, and a certain number of bits to say where with that number of decimal place called, it is called as exponent. In the floating point number representation of a number has two parts. The first part represents signed fixed point number is called mantissa, and the second part designated position decimal this point is called exponent. See, it is the mantissa exponent sign bit. Okay, so mantissa exponent sign bit. Suppose the number is from the different of bits sign exponent and 23 bits fractional part, the leading bit 1 is not stored with always. See, for example, minus 53.5 is normalized, then 53.5 and is the minus 1 point is represented to the below. See, minus is 1 and exponent part is 1, 2, 4, 5. It is exponent, it is a mantissa size of 53. So likewise you have to assign it. So in that way, in representation, we cannot reserve a specific number of bits for the integer part or the fractional part. Instead of it reserves a certain number of bits for the number. And next one, register, transfer and micro operations. Okay. In register, transfer and micro operation, the first one is the micro operation and register transfer. Okay, so what is the micro operation? The operations are executed on data stored in registers is called as a micro operations. Okay, a micro operation is an elementary operation to performed on the information stored in one or more registers. The regime of the operations in many replace the binary information of register or may be transferred to the other register, and various micro operations are shift, count, clear and load and so on. Okay, and what is register transfer? Computer registers are designated by the capital letters to denote the function of the particular registers. For example, the register that hold the address of the memory units is usually called as a memory. Okay, then in register transfer is we can transfer the data from one register to the another. Here we can use the different type of register, that is MAR, memory address register. Other designated registers are program counter, increment register and R1, the register name. See, the basic symbols for register: letters denotes register MAR, R2, and parentheses, that is denote a part of registers. Okay, and arrow denotes the transfer of registers R1 to R2, and comma separate of two micro operations, that is R2 to R1, comma R1 to R2. So different type of symbols we can use here. So letters are denotes register MAR, that is memory address register, and register, and parentheses it will be part of the register, and arrow denotes transfer of information, comma separate two micro operations R2 to R1, comma R1 to R2. See, the registers are designated with capital letters, that is PC, program counter, MAR, memory address register, memory register and IR, and TR. Okay, so what is that block diagram of register? That is R1 and showing the individual bits 0, 1, 2, 3, 4, 5, 6, 7 and number of bits 0 to 15 is R2 and divided in two parts, program counter L and H. Okay, see, a statement that specific register transfer from input is available from output of the source register to the inputs of the designation registers and that the destination register has a parallel load capability. Normally we can transfer to occur the data of the registers. Okay, and the if then statement. Okay, then register transfer statement. A statement that specifies a register transfer implies that the circuits are available from the output of the source register to the input of the destination register and the destination register transferred to the load capability. Normally we have transfer the occur only when the perimeter or condition. This can be shown by the means of if then statement. If P equal to 1, then R2 to R1, where P is the control signal is generated in the control sections. If normally in programming language, if then, if the condition is true, then it will be transferred 1, otherwise it go to the else statement. Likewise, if here P equal to 1, then P is a control signals, it will be generated to the in the control section, and a control function is a boolean variable that is equal to 1 or 0. The control function is included in the statement as follows: P colon R2 to R1, T R2 to R1, R1 to R2. Okay, and every statement written in a register transfer notation implies a hardware constructions of implementing the transfer. The following diagram that depicts the transfer from R1 to R2. See here, control circuit P, load R2, R1, then P equal to 1, then R1 data will be transferred to the R2. See here, transfer from R1 to R2 when P equal to 1, that is when P equal to 1, that is control for unit is P equal to 1, then R1 the data the transfer from R1 to R2. Okay, the n outputs of registers are connected to the n inputs of register R2. The letter n will be used to indicate any number of bits of the register R2 has load the input that the accumulated by the control variable P. It is assumed that a control variable is the variable synchronized with the same clock as to the circuit. See here, this is the clock and it is load. It is a transfer to the occurring here. The P is accumulated the control section by revising the address of the clock pulse time t plus 1 time t. The next position of the transferring the clock at the time of t plus 1. Find the load input active and data input R2 then loaded into the register in parallel. When T code activated, the data will be loaded into the T plus 1 and the T plus 1 finds the load input active and data inputs of R2 loaded into the register in parallelly. That is called as the timing diagram. See, these are the registers R1, they're showing the individual bits and number of bits and divided to the two parts. Then register transfer statement is R1 to R2, then R1 data will transfer to R2. That is, if P equal to 1, then R1 to R2. It will be assigned P colon R2 R1. That is, whenever the control circuit P equal to 1, then R1 is transferred to the data into R2. Here we can assign to the n, it will be used to the indicate any number of bits for the register, and register R2 has load input that accumulate the control variable of the P. Okay, and likewise we have to use the clock system at the pulse of it time t, the next position transition of the clock times t plus 1 find the load input active and data input of R2 then load into the register in parallel. Okay. Next, bus and memory transfers. The common bus scheme can implement it in two ways. First one is the using multiplexers and using three-state bus layers. Okay, so here a digital computer has many registers and paths be provided to transfer information from one register to the another register. Okay, the number of bus wires will be excessive with separate lines used to the between each register and other registers in the system. See, whenever we have to transfer data from one register to another register, we can use the number of connections, number of wires. It will be excessive. In that process, we can use the multiplexers. Okay, see, a more efficient scheme to transferring information between registers in a multiple register systems configuration a common bus system. One way considering the common system is we can use the multiplexer. Okay, the multiplexer select the source register whose binary information is placed on the bus. The construction of a bus system for four registers, that is register A, register B, register C and register D, that is A0, A1, A2, A3, B0, B1, B2, B3, C0, C1, C2, C3, D0, D1, D2, D3. See here, A0 correct to multiplex 0, B0 correct to multiplex 0, C0 correct to multiplex 0, D0 correct to multiplex 3. Okay, so for example 1, 2, 3, 4, A0, A1, A2, A3. So 1, 2, 3. These are the 4 bits. 1, 2, 3, 4, 5. So whenever 1, 2, 3, 4, 5 means A0, it will be activated the multiplex of 0. And next bits it activated to the multiplex of 1. The next bit activated to the multiplexer 2. The next bit activated to the multiplexer 3. See, the construction of a bus system for 4 registers and each register has the 4 bits number of 0 to 3. The bus consisting of 4 by 1 multiplexers, each having for the data inputs 0 to 3. So 0, 1, 2, 3, that is A0, B0, C0, D0, A1, B1, C1, D1, A2, B2, C2, D2, A3, B3, C3, D3. See here, and with the selections of input S1 and S0, 0, 0, then the register A is selected. Then S1, 0, S0, 1, B register is selected, and S1, 1 and S0, 0, C register is selected, and S1, 1, S0, 1, then D is selected. Okay. So for example, output of one register A is connected to input of 0 of multi-1 because this input is labeled as A1. Thus multiplex 0 multiplexer the 4 0 bits of the registers and multiplexer 1 4 1 bits of the register, and similarly for the other 2 bits multiplexer 2 and multiplexer 3. The two selection lines of S1 and S0, see this is S1 and S0 are connected to the selection of inputs for all 4 multiplexers. The selection line of the choose 4 bits of one register and transfer to the 4 line of common bus. See for example S1 S0 is 0 0, the data inputs of all 4 multiplexers are selected 0 0 0 0 from bus. This causes the bus lines are receive the content of register A. Likewise S1 S0 0 1, S1 S0 1 0, S1 1 D. Likewise we can go to A, B, C, D registers are selected. Okay, the transfer of information from a bus into one of many destination registers can be accomplished by connection of the buses and accumulated to the load of the particular system. And destination registers are used to the transfer of the information and particular destination of the per line transfer many to the bus. That is C to bus and bus to R1 or C to R1. Okay. So in that way, it may be convenient to the transfer to the C to R1. So why we are using the multiplexers? When we have to transfer one register to another register data, it may be the number of connections will be excessive. In that way, we can use the multiplexers. Here we can use register A, register B, register C, register D, and register A0, B0, C0, D0. It will come to the multiplexer 0, A1, B1, C1 divided to 1 multiplexer 1, A2, B2, C2 in multiplexer 2, A3, B3, C3 multiplexer 3. Whenever the states that S1 is 0, 0, 0, then register A is selected, then 0, 1 B is selected, and 1, 0 C is selected, and 1, 1 D is selected. Okay, this is the 4-line common bus. And also we can use the 8-line common bus, we can use the 16-line of common bus also we have to use to implement the bus and memory transfer of the particular system. So the common bus scheme we can use the implemented in 2 ways. The first one is using multiplexer and second one is using 3 state bus layers. Okay. The bus for the 4 registers. This is a 4-line common bus. These are the 4 registers. These are the 4x1 multiplexer. That's the multiplexer 0, multiplexer 1, multiplexer 2, and multiplexer 3. These are states S1, S0, S1, S0, 0, 0. The register A selected, S1, 0, S0, 1, B selected, 1, 0, C selected, 1, 1, D is selected. Okay. And next one is 3-state buffer. That is, a bus system can be constructed with 3 state gates instead of multiplexers, and 3-state gate is a digital circuit that exhibits the 3 states of 2 of the states or signals equivalent to the logical 1 or 0. In a conventional gate, the third is the high impedance state, and third one is the high impedance state. The high impedance state behaves like an open circuit, which means that the output is disconnected and does not have a logical significance. Okay, 3-state you have many from the conventional laws such as and non-gate. Okay, this is a gate. You can use input A, input C, and output Y equal to, if C equal to 1, and high impedance state if C equal to 0, that is the output is disconnected and does not have any logical significance, it will be go for the high impedance state. Okay, it is a graphical symbol for the 3-state buffer. If you can use in AND or NAND gates. Okay, when the control input is equal to one of the output is enabled and the gate has behaved like any conventional buffers with the output of the particular instructions. Okay, and when the control input is 0, it goes to the normal independent state. The high impedance state of the 3 gates provided a special feature not available in other gates. The construction of the bus system with the 3-state buffer is demonstrated as likewise. See here, S1 is 0, select and E is enable. We can use the 2x4 decoder and we can use the 3-state, that is the A0, B0, C0, D0 and 0, 1, 2, 3. Here the output of 4 buffers are connected to the from a single bus line, one way to ensure that the no more than one connected to the another input. When enable input of the decoder of 4 outputs are 0 and the bus line is in high impedance state, and after, because all buffers are disabled, when the enable input is active, one of the 3 states of the activated and it will be transferred to the data, and the binary value is the select inputs of the decoder. So it is the one of the 3-state buffer. Here we can using the, in common bus we can use the 2 types. So The common bus scheme can be done two ways. The first one is the using the multiplexer, and second one using the three-state bus layers. Okay, in multiplexer we can use the 4 multiplexer. In the three-state buffer we can use the one of the decoder. We can connect to the different type of bus line bits. Okay, it is in a high impedance state, it will be disabled. When the enable is activated, one of the three-state buffers will be activated. Okay.